já pode começar, né, Luiz? Você que conduz aí, tá?
Okay. Okay, so good morning, everyone. So we'll try to speak in English because we are transmitting to YouTube. So my name is Luiz Rodrigues. I'm from the Western Paraná State University in Cascavel, Paraná, Brazil. And in partnership with Professor Aldri, Luiz dos Santos from the Federal University of Minas Gerais, we proposed this first workshop on security, privacy, and reliability on wireless sensing networks, WSENSING. So unfortunately, Professor Aldi cannot be present today, but he has sent his greetings. So as we pointed out in the workshop presentation, current wireless sensing networks are widely used in a range of applications, such as agriculture, healthcare, smart cities, and so on. And with big new challenges, with the emergence of cyber-physical systems and cyber-human systems, especially in the context of the Industry 4.0. So the WSENSING workshop aims to bring together leading researchers and practitioners from academia and industry to advance the state of art and to identify open challenges, of course, on security, privacy, and reliability in the range of wireless sensing networks. So before we start this session, I would like to thank you, the event organizers from the LADC, especially Ambrosio, that is here with us, and Nuno Laranjeira for coordinating the workshops. I'd like to thank you as well the program committee, who did an extraordinary job for reading and giving suggestions on the papers. And we are especially grateful to the authors who submitted excellent papers, and which will be discussed now in this session. So Anna, would you like to say some words, or could you start?
Yes, just to thank you for all the efforts in organizing, in conquer people to write the papers and providing this subject to be discussed in LADC. Just to thank you and have a good discussion.
Okay, thank you again, Anna, for being here. So I think you're ready to start. So the first paper, we have 4 papers in this section. So the first paper is from the Federal University of Paraná. The authors are Fábio Angel de Camargo, that will be present, and Elias Duarte Jr. So the title is A Down-to-Earth Scheduling Strategy for Dense SCNR Wireless Networks. So I would like to ask Hoffman to play the video, and then after that we can discuss a little bit about the work.
Hello, I'm Fábio. I'm a PhD candidate at UFPR under the supervisor of Professor Elias Duarte. This is the presentation of a work entitled A Down-to-Earth Scheduling Strategy for Dense SINR Wireless Network. The presentation is divided into 4 sections. In the first one, I will introduce a model widely used in wireless network called the SINR model. In the second section, I will describe a scheduling strategy based on the SINR model proposed by us. Next is show the strategy evaluation in section 3, and finally the conclusions of the work are in section 4. In order to obtain results that capture the properties of a wireless network, much care has to be taken when choosing the communication model. A most important lesson in a wireless network is that concurrent transmission may cause interference. In a wireless network, if 2 main devices transmit at the same time, the interference caused by this transmission will prevent an intended receiver from receiving the signal, that is, the message is lost. The SINR model is widely used mainly for considering cumulative interference on signal reception. This model has a criterion to say if a signal can be correctly received. This criterion is based on 3 properties: signal propagation, noise, and interference. A signal only can be received if the ratio between the received signal power and the sum of the power of all interfering signals, here we call tau, plus the noise must be greater than or equal through threshold gamma, which is called SINR threshold, specified as this inequality. In this inequality, we have Pt as the transmission power. The function dij means the distance between I and j. Alpha is the path loss exponent, which depends on the considered environment, and finally N0, which represents the background noise. A way to deal with interference is to define a schedule for the transmissions. In a schedule, the time is divided into sequential slots. Each device is scheduled to transmit in a time slot, and all devices have to be assigned. It is possible to schedule simultaneous transmission by devices that are reasonably far apart. This is called spatial reuse. About our strategy. We have been reading and studying schedule strategy in the SINR model, and we realized that most of the work in this field has been theoretical. So, we decided to propose a simple schedule strategy under the SINR model that could show through simulation. This strategy assumes that devices can estimate the mutual interference based on device and positional knowledge. Thus, it becomes possible to know which devices can transmit simultaneously and get spatial reuse. In the end, the strategy produces as output a TDMA schedule. Some important assumptions. Each device is scheduled to a time slot and only communicates with the closest device. There is an initial phase where the device transmits your ID and position. The transmission power is individually adjusted. It means we don't use uniform power transmission. About the power transmission, the SINR inequality can be used to estimate the minimal power necessary so that the signal could be received in the absence of other transmission. To do that, we isolate the power transmission in the SINR inequality and transform it into inequality, as shown in this frame. But, in order to have simultaneous transmission, the transmission power levels must be set so that the SINR condition at each receiver is above the limit, not at the limit. So, we insert a constant called gamma spare to all devices. In that way, each device computes the minimal power necessary to achieve a SINR threshold plus a SINR spare. If the SINR spare is common to all devices, they all can estimate the power receptions. On this frame, we have an example scenario with 10 devices randomly distributed in space. It will be used to better explain the proposed strategy. Each device computes a beta set. If the received power of the transmitter K, considered an interference device, is less than the interference supported by J, then K is added to the beta set of device I. So, in beta I, we have a list with devices that can individually transmit at the same time that I, and yet the J device receives the E signal. Considering the example scenario, we have this beta I table. In the second line, for example, we have device 0 send a signal to device 6, and we know that 3 and 5 can transmit individually at the same time that 0, and yet 6 receives the 0 signal. Next, it is checked if more than a single device can communicate at the same time with I. Following the same example, we know that 3 and 5 can transmit individually with 0. It means the individual interference of 3 on 0 is insignificant, and the interference of 5 individually is too insignificant. We need to know if the cumulative interference of 3 plus 5 can prevent J to receive the E signal. If the cumulative interference is below the maximum interference supported by J, this set is added to the I list. In this example, the cumulative interference of 3 and 5 can't prevent the signal reception by J, so the set with 3 and 5 is in the TI list of 0. The combination of all elements in beta must be checked to create this TI table. At this point, we want to discover which transmitter can transmit at the same time, and yet your respective device receives correctly the signal. So, for example, for a given device I, TI contains the set with X and Y. For the three devices I, X, Y to transmit at the same time, it is necessary that I and Y be in TX and that X, I be in TY. If this is true, the set with I, X, Y is added to a delta list. In the delta list, we have all sets of transmitters that can transmit at the same time with guaranteed reception. For the example in progress, we have the delta list shown by this frame. Now, to produce a schedule, we have to select a limited number of sets in delta and assign each set to a time slot. Note that a device can be in multiple sets. Therefore, it is necessary to properly choose which sets to schedule to obtain a schedule that is efficient, in particular in terms of spatial reuse. To do that, we create an undirected graph G-delta from delta list. Each vertex is an element in delta, and there is an edge between a pair of elements only if they have a device in common. Next, algorithm runs to find the largest independent vertex set of G-delta, called S. This guarantees that the same device is selected at most only once. Each element set in S is scaled to transmit in the same time slot. Devices that remain not scaled up to this point must be assigned to individual time slots. This is done following the ascending order of their identifiers. The final schedule for the example is shown in this frame. Note that 10 devices were scaled into 6 time slots. We evaluated this strategy through simulation. For this, a wireless network simulator under the SINR model was implemented using Omnet++ and iNet framework. We look to evaluate the strategy under different densities. For simulation, we consider that 10 devices randomly distributed across the two-dimensional plane. Different densities levels, 10 by 10, 25 by 25, 50 by 50, and 100 by 100. A total of 6,000 different placements of the devices were considered. This figure shows for different densities the respective percentages of the size of the schedules. As expected, the higher densities, as in the 10 by 10, has minor spatial reuse, which means more slots are necessary. As the mutual interferences increase, it becomes more difficult to have simultaneous communication. In less dense scenarios, such as 100 by 100, 23% of the experiments resulted in schedules with 5 or 6 slots. This can be considered a very efficient schedule, which reduces by 50% the number of time slots necessary. So, in order to evaluate the algorithm only in scenarios where it's possible to have simultaneous communication, we ignored in this figure the scenarios which needed 10 slots. As it's possible to see, the sizes of the schedules obtained by the strategy for the different scenarios are not really very significant. For the scenarios of 100 by 100, 50 by 50, and 25 by 25, the percentage of schedules with 5 to 9 slots are quite similar. The differences are of at most 1%. The percent is only more significant when a much denser scenario is used. Comparing the most with the least dense scenario, the percentage of schedules with 5 slots increases from 0.9% to 3%, while the schedules with 9 slots decrease from 12.7% to 6.5%. The results make it clear that the strategy is effective. It takes advantage of spatial reuse and can be used in wireless communication networks of different densities. Finally, the conclusion. We presented a schedule strategy for wireless network under the SINR model. This is a practical strategy that could be implemented and evaluated through simulation. The results show that an effective schedule can be created for different wireless network densities. This is it. This is my email. Thank you for your attention.
Okay, thank you, Fabio, for the nice video. So, welcome to the WSENSING. So we have time for questions. So in the time that questions are being formulated, Fabio, could you tell us a little bit more about the work, the context that you are developing this job, or highlight some important things that you want to say?
Okay. Good morning, everyone. We have been working about strategy of scheduling in wireless network, and mainly in the SINR model. And in all papers that we find, we think that the most of them are about highly theoretical. So we try to make it something simple that could be showed about through simulation. We have been studying and try to make another scheduling algorithm like to be my PhD thesis.
Okay, very nice. So are you planning to compare this solution with another one, or do you have another solution that you can talk about?
At this time, no. You just compare with our baseline is that if there's no schedule, they need a total number of devices to schedule to this time lot. So at this point, we don't think yet, but sure, you can use another algorithm to try to compare.
Okay, so we have a question from the audience. So Hoffman asked about the lifetime of the network. I think you can see in the chat. A different strategy for limiting the transmission to the closest node is also valid in your algorithm. So for instance, considering a dynamic space distortion based on the available battery level at each node. Even though node A is closest to B, C selecting the next hope of B as C battery level is higher than B. So
the energy is something very important, but at this time we don't consider that. We just assume that battery is endless. But sure,
okay.
it's something important. We try to reduce the power used by choosing the transmitter to transmit at the device that is closest to him, to it. But at this time, we don't have a study about the energy efficiency of the algorithm. But sure, it's something important that should be considered.
Okay, very good. Okay, Hoffman, so thank you for the question. Just one last question. So you said that the difference on the sizes of the schedules are not really very significant. So could you talk about a little bit more about this?
What? I'm sorry?
You said in the paper that the difference of the size of the schedules obtained by the strategy for different scenarios are not really very significant. So there's some reason for this, or do you have any idea?
In dense scenarios, is difficult to have. It's difficult to schedule the devices because the interference caused by them is something that can interrupt the device to receive a message. So you show that with this algorithm, the final result is not so different of when the scenario is not so dense. It can be used so in scenarios dense, so like not so dense.
Okay. I think we have time for our last question. Federico asked, could you see the question there?
Sure. I don't know if there
I
is.
don't know if that's a question for the paper. Yeah.
But cycle. What is that? I'm sorry. There's a problem with that cycle. We first assume that there is an initial phase where all devices have to disseminate message with your ID and position. At the first phase, we assume that devices use some access medium like CSMA, CA, for example. Succeed next, the device you have to use like a TDMA access medium.
Okay, maybe you can talk a little bit more offline of this.
Okay.
Thank you, Frederico, Hoffman, for your questions. So thank you, Fabio. Nice work. Send my greetings to Elias. As you know, he was my advisor as well. So
Yeah.
we have a great collaboration till now. So thank you again, and we need to go to the second paper now. Bye.
Okay, thank you.
So the second paper of this section, let's just check if I have the right order. So the second paper is from the Aeronautics Institute of Technology. The authors are Gustavo de Carvalho Bertoli, Lourenço Pereira Jr., e Osamu Saltomi, about classification of denial of service attacks on Wi-Fi based unnamed aerial vehicle. So let's see the video and then we can forward to questions.
Hi, I am Gustavo Bertoli, and I will present our paper Classification of Denial of Service Attacks on Wi-Fi based Unmanned Aerial Vehicle. This work was performed with my advisors, Lourenço Alves Pereira Jr. and Osamu Saltomi. The agenda for this presentation will start explaining the context and the challenges faced by the Wi-Fi based UAVs. I will discuss the framework and the experimental setup based on this framework to perform this research. Also, the obtained results will be presented in conjunction with the next steps and conclusions from this work. Regarding the context and the challenges that motivates our research, the first fact is that the top sellers drones are the Wi-Fi based ones. This design approach takes advantage of mobile phones for controlling the drone through Wi-Fi communication. In this case, the UAV normally acts as the access point in this communication. By using these well-known protocols and due to the lack of security by design, most of these consumer products also inherit the well-known vulnerabilities of the wireless protocol. So, security measures must be in place to avoid catastrophic incidents during operation. Some examples of these catastrophic incidents could be the crash of the drone, collision, or in some case the takeover of the control. Our paper bases in a three-step framework. The first step consists of a data capturing phase, and this phase aims to capture all network traffic between the controller and the UAV during normal operation and between an attacker and the UAV. In our case, this network traffic is the Wi-Fi communication between those agents. With the traffic obtained during data capturing step, we have a dataset composed by these network packets, and from this step we initiate machine learning development to obtain an algorithm that learns from this data how to determine if a traffic is legitimate or malicious. The last step of our framework is the deployment of these algorithms in the UAV. However, this last step is not in the scope of this presentation. The drone under test in our paper is the well-known Parrot AR drone version 2. This UAV have a lot of public information and previous publications from cybersecurity and robotics domain. This drone uses the Wi-Fi protocol for both controlling the drone using the UDP protocol and for data transmission, such as video, over TCP protocol. Also, this UAV runs on embedded Linux, and this technical design makes possible the implementation of the machine learning based security measures envisioned by this paper as Linux kernel modules. To create our dataset, as explained during the data capture step, we use two scenarios. First, the normal scenario that we stimulate, for example, multiple connections, in other words, handshakes between the UAV and the controller, that is in our case a mobile phone. We also perform multiple commands for takeoff and landing of the UAV, and another normal scenario is a full flight. This full flight represents random flights performed to capture the traffic. For the denial of service scenario, we start with multiple de-authentication attacks, and this attack represents a malicious agent performing a de-authentication attack impersonating a legitimate user. It's important to highlight that the de-authentication is a functionality available on the EEE 802.11 protocol that is misused in this threat scenario. Next, we perform a UDP flooding attack, and this flooding attack sends a huge amount of UDP packets to the available services, and once no defense is in place, this results in a denial of service and affects the availability of the UAV. Finally, a TCP flood that is similar to the UDP flood attack, and this TCP flood also represents the denial of service with the affecting directly the availability of the UAV. In summary, from the exercise scenarios, it results on a dataset composed by 473,000 packets. From these total packets, 97% represents the normal packets, resulting in an imbalanced dataset. It is important to mention that this imbalanceness is a characteristic of the cybersecurity domain. The de-authentication packets represents 1.8% of the dataset, and the flooding attacks represents around 1.2%. As part of the machine learning development, the definition of the applicable features for this learning task were obtained through an exploratory data analysis using the Wireshark application. From this exploratory data analysis, it was visually possible to determine two features that separate the normal and the malicious packets. These features are the time delta between two consecutive frames in seconds and the frame length in bytes. Our understanding is that the deterministic behavior of the communication for an UAV in comparison with the attacks makes possible to simple features distinguish between the two classes. In this machine learning development, we also did some design decisions as follow. We opted to use algorithms that are interpretable once we consider the deployment of the trained models in the embedded Linux on the UAV. We also simplified the learning task to be a binary classification problem, with the packets being classified as normal or malicious. And finally, we used a stratified split to keep the imbalances of the dataset that we created. And also we choose a 60%, 40% train test split. The two algorithms evaluated by us were a decision tree, a shallow decision tree with maximum depth of 3, and the logistic regression. This decision is based on the premise of an interpretable model, and also these models presented good results on our preliminary studies. These are the results obtained for both algorithms. In a first glance, we can understand that both algorithms present a good accuracy, but due to the imbalances of our dataset, we cannot rely just on accuracy to opt between the two algorithms. From a data problem perspective, we understand that the decision tree performs better than the logistic regression. This understanding can be confirmed by the other metrics that takes into account the imbalances of the dataset created by us, for example, the F1 score and the false positive and false negative rates. Just to be clear, the F1 score calculated in our work considers the positive class being the malicious packets instead of the normal packet. We also evaluated the latency for inference of both algorithms. This is an important metric to be taken into account once we are considering the deployment of these trained models on the UAV. In this case, the calculation of the latency was performed on a laptop computer, and these values were obtained during the inference over all the test set and not just the inference over one sample. But these values are useful to compare both algorithms. From this data, we infer that the logistic regression has a lower latency in comparison with the decision tree. This is aligned with the complexity of the algorithms, with logistic regression being a simple parametric model and the decision tree a more complex model. However, we must remember that the logistic regression presented a worse performance when considering this as a data science problem, and in this case further analysis must be done to determine the minimum acceptable latency for the UAV controller. Summarizing our findings, we understand that simple and interpretable algorithms such as shallow decision trees and logistic regressions are capable to detect denial of service attacks on these Wi-Fi based UAVs. We also understand that further analysis of the latency requirement must be performed to determine the weight of this characteristic during a trade-off analysis. We have as next steps the translation of these trained models for deployment in the UAV for operational evaluation. So thank you for your attention during this presentation, and here follows my email for further discussion or clarification or any needs regarding this publication, and also the link for our repository that contains the generated dataset and the code to reproduce this work. Thank you.
Very good. So thank you, Gustavo. Could you join us to the discussion?
Hello, good morning.
Hello, good morning. Welcome. Okay, we have time for questions, so please, you can write in the chat or use your microphone to ask. So in the meantime, Gustavo, could you explain more about the methodology that you use to capture data and to inject or simulate attacks in your data?
Okay, so we used a technique called sniffing. So we configured a laptop computer with an extra interface, Wi-Fi interface in monitor mode. We call it to perform this task to be capable to read all the traffic. Then we perform all the flights in a rural area here in Brazil to do not suffer from interference from other devices in the area. And in this area, we perform the flights, the connections, the handshakes between the controller. In this case, we have 3 participants. I mean, the UAV in the case, the mobile phone, and the computer that performs the recordings of this traffic in this environment. Then we used a second interface on the same computer to perform the attacks. So through the MAC address of those agents, the 2 interfaces on the computer, the UAV and the mobile phone, we were capable to filter all the traffic that we captured. Okay, very clear now. So you said in the end that the data is available in a repository. So we have how big is this set? Yeah, so this data set that is available on our repository is just the 2 features that is used in this work, and we are around some gigabytes, but we have to perform, I mean, gigabytes, the original files, the PCAP files, prior to any filtering. So we envision this as a possibility in the future to make this data set, the full data set, available to make our other researchers to use that. But once we did not perform this, the cleaning of the data, I mean the images that the drone take from the tests and things like that, we are not making available the raw data set, but just the data set with the 2 features that we used in this paper. Okay, very good. Do you have any questions for the audience? So I have one more question. So you choose to use 2 algorithms to test your solution, like logic regression and decision tree. So have you considered to use the other algorithms, even if just for comparison? Because we know that many algorithms are demands really high computing power now. So have you considered to compare with another one? Yeah, we did just to evaluate the performance. We tested a 2-layer neural network, a not so deep neural network. But the question is, the context of this work is that we were envisioning the deployment of the models. So we did this in past work, in past publication, using the Linux kernel modules to translate a trained model to be embedded on the computational device. So we restricted the scope in models that are possible to make and easily to make this translation from the trained model to the software application. So this is the context for the decision, but we evaluated a neural network. And for using those specific features and for this specific detection, the decision tree outperformed the neural network also.
from a data perspective. We did not evaluate the latency in this case.
Okay, so in practice you can also train the network offline and then input in the device, right?
Yes, yes. So when we consider more complex models, for sure we have to understand how to implement that. Currently, we have some light deep learning models for TensorFlow Lite and so on. That is possible to translate a more complex model, but once we are considering a very restrictive device, we did not consider this possibility.
Okay. So, do you have any other question? No? So, thank you, Gustavo, for coming. Thank you for sending your paper. And
thank you all.
Okay.
Bye-bye.
Bye. Okay, so we have the third paper. It comes from the Western Paraná State University, UniOeste. The authors are Leonardo Vanzin and Márcio Yamada. So the title is Calibration of BLE Beacons and its Impact on Distance Estimation using the Long Distance Path Loss Model.
Greetings, my name is Leonardo, and with Márcio, we are from Western State University of Paraná, from the course Computer Science. And I'm going to talk about calibration of BLE beacons and its impact on distance estimation using the log distance path loss model. Everyone has at least one device, can be big or small, that is connected to a network. This network can be, for example, Wi-Fi or Bluetooth. And in the last few years appeared the Bluetooth 4.0, that is the Bluetooth Low Energy. And with it also came the broadcasting mode, that allows devices to send information without the need to be connected, and because of that, the power consumption is low. And this opened the opportunity for Bluetooth beacons, that are small devices that send package with information to another compatible device, and as they use Bluetooth Low Energy, they can work during months or even years with only one coin cell battery. One thing they can do is the indoor location, because GPS can work properly in indoor spaces. They can't tell in which room you are. But you can use beacons, and positioning them strategically in the space, a person's smartphone can detect them, and with an application, it can determine the person's location through the trilateration method. This technology can be used by companies or stores to provide a better service for their customers. The object of this work was to prototype an 8M10 board as a beacon and evaluate the log distance path model in order to estimate the distance between the users with a smartphone or tablet and the beacon. The material used were 3 HM10 board, 1 Li-ion battery, a major type, an open or big space, and the application BLE scanner that was running on an Android smartphone. After that, 1 HM10 board was connected to the battery and was placed on the space. Then the measured type was open in a straight line. This one that we use have 5 meters. And we used the BLE scanner application in each half meter to collect 10 RSSI values. RSSI is the received signal strength indicator that is sent by the beacon and received by the smartphone. Then was calculated the average of the 10 RSSI values that was collected in each distance. Here is another screen for BLE scanner where you can see this negative number is the RSSI value. So each of this circle is one device. As you can see, the closer the device is from the smartphone, more positive is the RSSI number. And the farther the device is from the smartphone, more negative is this number. After data collection, this value was used on the log distance path model equation. In this equation, we can see which should be the RSSI value for each distance. The RSSD0 is a constant that uses a RSSI value of a determined distance. In this case, we use the RSSI value of 1 meter. That after some calculation, we found that the RSSI value for 1 meter is minus 70 dB. Tn is the path loss exponent. It will model the environment interfaces to avoid things that could interfere with the signal. And how we use a big open space is recommended to use the n equal 2. The d is the distance, like 0.5, 1, 1.5 meters. And the d is the distance used on the RSSD0, that in this case is 1. Then we did that for all the 3 boards. But sometimes this n does not describe well the relation RSSI distance, so we can calculate an appropriate n using the same equation, but writing it differently. The RSSD0 is the same value. The RSSI is the average of those 10 RSSI values collected in each distance. And the d is the distance. So when you will calculate for the distance 0.5, you're going to use the average of the 10 RSSI values collected in this distance. We do that for all the distance, so we will have an n for each distance. Then we calculate the average of these n's to find the n for that specific board. Then you do the same thing with the other boards. After finding the n for the boards, we replace the n equal to for this n that was calculated. After do all the calculation and get all the results, they were placed in graphics. The blue line is the RSSI values that should be in each distance using the n equal to. The green line is the RSSI values that should be in each distance using the calculated n, that in this case is 3.44. And the red line is the average of RSSI values that was found in the real measurement during the experiment. The HM10 has identifiers. They are the major and the minor. In this case, the major is the same for the 3 boards, but they have different minors. We have the minor 7, 8, and 6. For this one, that is the minor 7, we didn't have so good results because as you can see, the red line is kind of far from the lines. This table shows the estimated distance using the log distance path loss model according to this equation. Using the n equal 2, that is the recommended coefficient for open spaces, the estimation error was 150% in some cases. And using the calculated n, that is in this case 3.44, reduces drastically, especially the mean error that went from 65.50 to 15.93. In the minor 8, we had good results because as you can see, the red line is really close to the green line. In this board, the highest error was in the distance 4.5 with more than 120%. And as you can see, using the n equal 2.75, the errors decrease. And as you can see, in low distance, this difference is not that big. And the mean error went from 44.65 to 14.66. In the minor 6, we also had good results. As you can see, the red line is close to the green line, that in this case is 2.32. And the errors also decrease, as you can see here in the mean error, that went from 22.77 to 10.50. To conclude, the HM10 can be used as a beacon because of its availability, low cost because the price is normally between $2 or $3, and because it's easy to prototype. That means it's not so complicated to configure the HM board to become a beacon. One thing was noticed is when the farther or closer the beacon is from the smartphone, the more imprecise is the calculated distance. Other thing is the RSSI variation during the collection, even with the smartphone completely static. And using a calculated end, we got better results because it can better model the environment, because there are some things that can interfere the signal, as Wi-Fi, other Bluetooth devices, or objects in the environment. For future works, we tend to study techniques to filter better RSSI values and implement trilateration method to determine indoor localization. Finally, I would like to thank MaxZoo for funding this scientific initiation project from the Cultural Education Program. Thanks. Any questions?
Professor Luiz, I think your microphone is muted.
Sorry. So thank you, Leonardo. So could you join us for discussion? We also have Professor Márcio in the room, so if you have any questions, you can do it now. Leonardo?
Yes.
Okay. I'm not seeing you. So Leonardo.
Oh, sorry.
Okay. So about the test that you have performed. So in your model, you have some data about accuracy. Could you explain a little bit more about this? Could you give us more details about your results?
So we tested the 3 M10 boards, and we saw a different accuracy between them. Because as you just watch it, this -7 was the one that had a little problems to determine the distance. But that was the objective of this test, is to evaluate if the HM board can determine the distance, and if the 3 HM boards they have the same they work the same, you know, they have the same efficiency.
Okay. So in your test, you have one source and one receiver, so one sync, and test this capacity to receive data, right?
Yes.
Okay. So different for the previous paper, you test in not in a farm, not in a separate place. So Bluetooth Low Energy use the same frequency from many other devices in 2.5 gigahertz, right?
Yes.
So do you think that the test could be affected by this other device? Have you did some comparison or have some data about this?
So that's why we used that equation, that the path loss model equation, that we have the N there, that model environment, to avoid these devices, Wi-Fi, other Bluetooth devices, or even objects that in the environment to interfere the signal. So with that N, we can have a better result. You know, can kind of exclude them, the signal, to have to see if how it would be if didn't have this interference.
Okay, so did you have a control about these other sources, right? In this experiment, right?
Yes.
Okay.
They say that normally we use the n equal 2 for open space, but we test it in a garage, so it's not it's a big space, but it's not an open space, and we are in an urban area, so we have this all interference. So that's why we calculate the n, so we can better filter this interference.
Okay, so you choose this strategy because it's well fit to your scenario. So, do you know if there are other possible equations or models that can be used, or are you planning to use this in your work?
Yes, as is the start of the project, so still have a lot to search, But yes, I tend to see other equations, other forms to get better results.
Okay. Any other question? No? Okay, so I would like to thank you, Leonardo, again. So I'm very proud of you. You are an undergraduate student and have a very nice work and a lot of things to do in your career. So thank you again for applying to the WSENSING. Thank you, Marcia, as well. And let's go to the last presentation.
Thank you.
So now we have the fourth paper from the Federal University of Juiz de Fora, and in collaboration with Federal University of Minas Gerais. Frederico Salles will present the paper and co-authored with Edelberto Silva, Alex Vieira, Marco Vieira, and Luiz Felipe Vieira. So the paper is about a proposal of a dynamic routing multicast protocol for visible light communication networks.
Hi, I will present the paper called A Proposal of a Dynamic Routing Multicast Protocol for Visible Light Communication Networks. First of all, I will introduce the authors. The first one is Frederico, a master's student, and Edelberto and Alex are from Federal University of Juiz de Fora and the advisors of Frederico. Marcos and Luiz are from Minas Gerais Federal University and collaborate with this paper. We would like to thank other agencies as CAPES, CNPq, FEPMIC. We have an agenda divided by 4 topics. The first one is about Wi-Fi, the Wi-Fi growth, residual effects, radio frequency misuse, and the other is VLC, about the visual light communication, and their advantages and disadvantages. After, we have our proposal, MCAS VLC, the multicast VLC, showing the multi-layer protocol, the MCAS VLC and its security and multi-hop scenario. And the last topic is our conclusion. The first one topic is Wi-Fi. In Wi-Fi we have residual effects. More than 100.5% increase of mobility devices from 2020 and 2025. So we can see in the table the world regions and the internet users. The growth is more than 2 times in this period. So overcrowded radio frequency spectrum, because Wi-Fi uses only the ISM frequencies, the 2.4 gigahertz and 5 gigahertz. So if we have growth of mobile devices, why we can attend other devices, new devices? So we can think in other technologies. For example, the VLC. As we can see in this image, we see the advantage about the VLC, or visual light communication. We can see the spectrum of visual light, and we have more space non-used in this case compared to Wi-Fi. So VLC can complement the internet access and at home, for example. So we can use it in industry or medical solutions. The VLC systems mostly use semiconductors, the LADs, as transmitters, due to their advantages and rapid developments in LED fabrication. Currently, the light on LEDs offers transmission bandwidth range between 20 MHz to over 100 MHz. Lighting offers many advantages of conventional lights, such as low power consumption, low cost, high luminance efficiency, long lifetime. So, for the reasons, the LEDs have become strong in the light market compared to traditional light solutions. So VLC can be a good way to complement the Wi-Fi technology, for example. In this slide, we see a typical scenario of VLC when we have one point as a main gateway and communicating directly with the end nodes. In our case, we have multi-hop, so we have the multicast VLC supported by VLC with multi-hop. So we can have management, a group management, for example, and we have alternatives of paths. And if a node, for example, does not belong to any group, it asks as a forward, for example, only forwarding the packet or the diagram for a group member. So in this case, when we have a group, we have a leader and I have end nodes and forward nodes, only to forward packets from one node to another node in the network with multi-hops. And visual light communication, we have intrinsic security because it's a passive security layer. So low cost implementation, color channel separation. If we use different colors for different clients, we have a slice to separate these clients. In this figure, we have the layers of VLC. When we see the user space with the application layer and kernel space with transport layer network layers, and we have the VLC, or our implementation, OpenVLC driver. The OpenVLC driver allows us to work with VLC MAC layer and VLC physical layer. So with a VLC firmware, we can talk directly with the hardware, the LED in this case. But it can be a disadvantage too. Little product to offer in the market, high sensible to interference by light sources, a shadow and physical barriers. All of this can increase the noise in this environment. But the technology continues to be interesting to complement Wi-Fi. Here we have our proposal, the multicast VLC. The multicast VLC is a multi-layer protocol using bottom the multi-hop algorithm to exchange the packets, and we have our proposal only to manage the groups, manage the packages, and slice the traffic for different groups. So in Multicast VLC, we have a reader based on eGMP v2, when we have the G message field, when we have all of the fields when you can see in the table on the right, on the bottom right, when we have the hexadecimals to represent it, and the other fields as max response time, checksum, and the group address. More important for us is group address and G messaging, because the other things it's not used in this time because we use only UDP for our tests. In the scenarios, you can see the group supervision when we have a multicast server, the main host, when send the traffic for the network, and we have the messages for group request and the group reply, and we have in blue the nodes represent the leader of the group, and the red is the hybrid node. It can be a leader or a end node or a forward, for example, and the end node. In both sides, we see two end nodes, XX and II. So we can see that the group is divided by using the IP range reserved for multicast. The 224.xx.2, for example, 224.xx.1. In our multicast protocol, we have the join message when the group member send a join group request for enter in a group, and the Lambda node and forward this message to the group leader, and the group leader advises the Lambda node, and the multicast receiving the message can put this node in an existing group. So reply this message, and all of flow can be forwarded from the multicast to this group member through the group leader and Lambda node, for example, a forward node. In this scenario, we have a flowchart for exit group when the multicast server send the multicast content and the group member receive the message, and after it advise that leave group for node X number X4 X24. So this message go through the group leader, and the multicast server receive this message, and forward it's okay, that this node is not in a group more. In this case, we have another thing, because the multicast VLC works with the Houghton spanning tree algorithm. So these routers use the BEL-114 protocol to determine the distance between themselves and the destination. So establishing the best routers and regularly exchanging the information with neighboring routers using the routing table. So we can use anything of routing protocols. In our tests, we use two VLC based on MRUDV, the same of the BEL-114 family. So here we only have the weights of the nodes, and we have the connection between them, and we have the connection the packets can pass through two ways or two paths, or if this node, the node in green, can turn off and the path continues to work because we have the nodes in red connecting the node in brown. So it's only to show that our protocol work managing group and does worry about the routing protocols. Here we have the multicast planet tree created by this mesh when we have a leader and a forward and a three end nodes. And we see on the right side the logical topology. Here is our testbed. We use OpenVLC, not 1.3 but 1.1, and we have this simple testbed to create a multicast server, a forward, a hybrid node that can be a leader, for example, and forward, and two end nodes. And really, this end node is only that works. The lambda is only to show that have another node, but not working in these tests. We will compare the multicast versus unicast in this scenario, because multicast is our proposal and the unicast is the normal traffic when all nodes receive all packets from the source. When you compare both scenarios, multicast versus unicast, we have only using 1 megabit per second in a bandwidth of about 6 megabits available. So we use only 1 megabit per second for multicast VLC, and unicast use more than 2 megabits per second. So the 2 times more than multicast VLC. Unicast use 2 more traffic, more bandwidth for compared to MCast VLC. So we have the distribution in the graph for the right side. When we see more condensed, the MCast VLC and the unicast is more sparse. Here in this graph is good to see how when a user entering a unicast scenario create the steps of here when we see 1 node, 2 nodes, and 3 nodes using all bandwidth available. But compared to MCast VLC, we use constantly 2 megabits per second. The only important in this case compared to unicast with multicast is that we have more leaders, we have more flows, more bandwidth, more necessary bandwidth. But in unicast, all nodes using more bandwidth. If you have 1, 2, 3, and n nodes, we have n times the bandwidth necessary to attend these nodes. But in multicast, if you have only 1 leader, we don't have any change to the bandwidth necessary. Here we have the conclusion about the main opportunities. We delivering data, no more data, but delivering data over agreements that prevent the lasting use of radio frequencies in Wi-Fi, as I told in the beginning, 2.4, 2.4 and 5 gigahertz is very full today, and we have opportunity to use other technology to complement the Wi-Fi. We have multicolor band derivation to isolate the multicast VLC if we want. For the future works, the multi-hop multicast protocol to VLC paradigm can be changed if you want, because it's not our focus in this work. Our focus is only to manage the group, and it's only with a negligible network overhead, reducing the bandwidth. So more good put, less halting, and unicast flow. So we only insert a network overhead, so negligible in this case. So the scalability is increased by our work in the LADC network. We would to thank you for watching and please keep in touch. Thank you.
Okay, thank you, Frederico. So, are we able to talk? Okay. Hello, good morning.
Morning.
Okay, we have time for questions, so please feel free to write or use your microphone. In the meantime, Frederico, congratulations on your job. It's a very interesting paper, even more compared with the previous paper when I talk about the overloading of some frequencies in urban area or etc. So even if you have a great interference we have also a high transmission rate, right? So could you talk a little bit more about the applications of your job, your work?
Okay, thanks. I would like my advisors and my collaborators. Thanks to all. My English is a little rust, so be kind, please. Consider some wrong words or typos in the job. I have to write it on work travel, so we could just work in so many fields: medical field, industrial, home, appliances. We could use to reduce, mitigate this noise, caused by misconfigured networks and overall the pollution. Then so many misconfigured routers, access points, drones now. 5V, it's so crowded these days. We need to give you a way to separate, not use just common frequencies anymore. So the main purpose is isolate these frequencies almost using higher frequencies. We could also separate the groups with color spreads, but it's it.
Okay, very nice. It's a real range of application, I think, from smart homes, smart cities, or even embedded system, right? So I remember that a couple of years ago, I saw a solution in a optical switch. So they are trying to make the communication faster in this device. So it's very so it avoids some noise, right? So completely embedded environment. So very nice.
We use embedded system. We use a backbone and open VLC. It's difficult to work with. It have a very little space to use. A Canon module is so little. You have to lose so many goodness, but it's working. It's working.
Okay. So more special. Sorry.
Good morning. Can you hear me?
Yes. Yes.
Let me test my PowerPoint. Oh, wait a minute.
It's coming, going. I can hear.
I'm I'm traveling with the laptop, so I don't have my usual setup here with. But let me see. Got it. Okay, normal. What is this? And then the video. Good.
Dr. Nancy, we are finishing the previous workshop.
Okay, it's a keynote for the next workshop,
Yes.
right? The next section. Sorry, Nancy, you're almost ready here. So in a few minutes, you can test your system, right?
Right. Okay, Dr. Nancy, we are just finishing the last workshop before you start.
Oh, okay.
Okay.
All right.
Just a minute, please.
Okay. Sorry. So Federico, talking about your solution. So you use a moodcast technique to test your algorithm. So is it a new technique, or you use some?
I have to make a hybrid. I use some HMP and some IP multicast solution. I have to throw off some solutions because we have so little space in kernel to apply the solutions.
So you make some adaptation, right?
Yeah, I used some HMP V2 solutions and some IP multicast, and the nodes sometimes act like a route with a tag ID, and the flow finds these tags and set of groups of interest flow, mount the multicast environment and the spanning tree, the multicast spanning tree, and then when check all IDs, all groups, we send the flow to these groups. There's also a leader group. Its main responsibility is maintain the group and inform the server that the group exists and need to receive some flow. So, more or less, HMP V2 with some IP multicast characteristics.
Great, very nice. So, do we have any other question, or just finish this presentation? So thank you, Federico. Thank you again for applying to the WSENSING workshop, and see you soon.
Thank you. Thank you all.
So, okay, you have finished this session. So once again, I would like to thank the workshop chairs, Ana and Uno, so all the program committee, so all the authors that have applied to attend this workshop, and all of you that are here in this conference. So it is the first workshop on security, privacy, and reliability on wireless sense network in the context of LADC. So I remember that all the papers will be available in IEEE digital library soon. So you could check these papers over there. So after the break, we have the last keynote speaker, and Nancy Leveson is already here. So I invited you, all of you to attend come back and attend these events.
Okay.
Thank you again, and goodbye.